This is going to be a very cool video and a system design video. Well, system design videos are my personal favorite because we get to discuss a lot of concepts here and all of them are almost always useful in a real world interview as well as designing softwares in the real world. So this is going to be pretty interesting because in this video we are going to design a job scheduler. Well, first of all, I will explain what a job scheduler is and why do we need it. Well, in different companies you can have a set of long running operations. Well, what is a long running operation? An operation which takes some time to complete is an LRO. For example, sending emails to hundreds of different users based on some different parameters maybe, or sending notifications to a set of users, or simply doing a code push and waiting for that code to be compiled, tested, etc. on the cloud. For example, if you just observe the CI/CD operations and when you push the code, it isn't scheduled immediately. It takes time to get scheduled and get run on the cloud, and when it has run completely and the testing is completed, it has some check marks that this code is bug free, it is tested, and all the tests are passing. So basically all of them are scheduled, they are not run immediately, and we can say that these are long running operations that take some time to be completed. In this video we are going to design a job scheduler which would be running some LROs, like long running operations. Let's get started. Basically we will have a backend, so we will also have a front end, but I'm not designing that here. I'm not like drawing another box to say that we will have a front end, but let's say that we have a backend. When the user requests the front end, sends a request, or it hits an API in the backend that this is the task that we want to run or schedule at a later point of time. So what we will do immediately is that we will save that task in the database first. Well, we can also enqueue inside a queue, but let's discuss that some other time. For now, I'm just going to save that task in the database. I will just call that a job that we are saving in the database. That job will have a job ID, a timestamp, a worker ID, and status. Well, what is a worker ID? I will come to that later. And status is the status of the job, and we can also have some metadata argument, or maybe it can be a script, like the job can be a Python script or a shell script that needs to be run. So we will just save that as an extra argument in the table. Now what we will have is a pool of workers. Well, these are just a set of machines that are going to pull the database, take the job from the database and run it on the bare metal or on the cloud, and then update the database again. So let's say that pool of workers are just some tens or thousands or hundreds of machines. It depends on the scale that we are trying to handle. Like if it is a very big fat organization, then we will need many more workers as compared to a small organization that can do well with 5 to 10 workers easily. So these pool of workers will be pulling the database, taking the job from there, and then running that job for a certain period of time. Well, we can also add another parameter to the table, which is retry count. That is the number of retries a job takes to be completed, because it might be a common case that one of the workers which is running a job shuts down due to some reason. Then in that case that job has still not completed, and we can say that if the job has not completed, then we need to retry it again. So basically retry count is simply the number of retries we are making for that job to be successfully completed. Well, as you can see, there are many problems with the system. First of all, this system is tightly coupled and all of the load is on the database. That is, the backend is saving the jobs to the database. The pool of workers, which can be tens, thousands, or hundreds of workers, are querying the database for the job. Then they are running the job, and then they are updating the database again with the status that, hey, this job is completed. This was a running state, now this is a completed state. So every worker is polling the database, every worker is updating the database, as well as a backend which can easily sit behind a load balancer, and we can have like multiple backends. They are also updating or writing to the database. So we have too much load on our database, and this is a bottleneck. So let's try to decouple this system. And well, this is a very common practice of decoupling the system. Basically the rule of thumb is that if you want to decouple two components in a system, you just insert a queue between them, and this is what we are going to do here. Well, we can have a service called task scheduler service, and the sole purpose of the service is to poll the database at different intervals and then enqueue the task inside a queue. For example, if we have a task of running a shell script like Python hello world simple shell script at every 10-minute interval, or let's say 10 p.m. IST or 10 p.m. GMT, whatever, then the task scheduler will poll the database, see that this task needs to be run at some point of time, and it will just enqueue it inside the task queue. And the pool of workers will now query the task instead of the database. But they're still updating the database. So they're still updating the database with the status of the task, but at least they are not querying the database all the time. So we have a task scheduler which queries the database, enqueues the task inside the task queue, and the pool of workers which are subscribed to the queue pull the task from there, they run the task, and then they update the database that the task is already completed. Now, there is a problem with this approach again. The pool of workers are still updating the database. So we have thousands of workers updating the database at one point of time, which we don't want. So we can decouple this again. We can have an updater microservice, and the sole purpose of the service is to update the database. So the pool of workers will now talk to the updater service, which is again maybe sitting behind a load balancer or something, which we can scale independently. So they will be talking with the updater service. The update service will be updating the database. It will update the database with all the retry count and everything. So let's say that a worker fails, then in that case, the worker won't be able to send heartbeat to the updater service. So how does the updater service work is something like this. We have a service, the updater service, and we have a pool of workers. When a new worker joins the pool, they will register themselves with the updater service, and this updater microservice will have its own set of database tables, etc. But I'm not going to dive into that detail. That is left as an exercise how it will work. Well, I can give you a hint that it's very simple and it's just a table to manage the entries of the workers. So now when a new worker registers with the pool, they will register with the updater service actually, and they will start sending heartbeat to the updater service. If for some reason a worker doesn't send heartbeat for some interval, the updater service will know that this worker is dead, and it will increase the retry count for that worker ID and for that job ID. And note that each and every job is picked up by a unique worker. So it's not the case that every job is picked by every worker, it is by a unique worker, and only in the case when that job is marked as failed and retry count incremented, in the case when the worker dies down and it is not able to send heartbeat to the updater service, only then that job is retried and picked by a new worker, and that worker ID is updated in the database. So we can see that the task scheduler is the one that schedules the task. The pool of workers subscribe to the task queue, pick up the tasks, and they run it, and these pool of workers are already registered with the updater microservice. The role of the updater microservice is to update the database, so we don't have a load concentrated on multiple work pools. This way the system is totally decoupled. Each and every service can be scaled independently. We can have like hundreds and thousands of workers. We can have updater microservice behind a load balancer, so that can be scaled by itself. The task scheduler can be scaled independently, like we can have different ones, but ideally we would prefer only one microservice which will just poll the database and queue the task to the task queue. The task queue can be an AWS SQS or some Kafka topic that we are publishing to. The pool of workers are subscribed to the Kafka topic or the SQS, and they will take up the tasks and run it, and the backend itself can be scaled depending on the number of tasks we are sending in the database. But what we can see here is now that our database is the bottleneck here, because everyone is dependent on the database. So what we can do is that we can just make this database as replicated or sharded. So if the database is sharded, our data is spread across different shards, and we don't have too much load on a single shard, but it is distributed across different shards. And since the database is replicated, we know for sure that it is fault tolerant. So guys, this is how we develop a fault tolerant, replicated and scalable system. Well, I'm using all the buzzwords here, but this is what it is. Now I will just go ahead and write some notes here to as well as describe the system. So user sends request to the backend with all the metadata, whether it is a script or some argument to a function. The backend saves it in the database, which is sharded and replicated and hence fault tolerant. The task scheduler polls the database and enqueues the job to a task queue. The pool of workers which are subscribed to the task queue pick up the job and execute them. These pool of workers are directly talking to the updater microservice, or we can think of some better name, but I think updater works for now. So these pool of workers talk with the updater microservice. They are registered with the updater microservice, which has set of all the worker IDs, and it keeps track of all the workers in the pool. The pool of workers, that is the workers inside the pool, keep sending heart to the updater service. If it doesn't receive some heartbeat from some worker, it knows that the worker is dead, increments the retry, and it marks the job as failed. And based on our logic, the task scheduler can decide whether to retry this job or not, so it will enqueue it back to the task queue. So this is how this whole system works, and this was a pretty interesting video with pretty interesting facts and concepts about distributed system, that how we can simply scale it. But before scaling, I would suggest that you make a correct system first. A system that works and that has no issues and that is correct is the system that we want to scale. We just don't want to start with the scalability, fault tolerant issues, but we want to make a system that works fine, because that is what we are paid for as a software engineer. We are paid to make correct systems. The scalability issue is already so you need to understand that we have AWS and other cloud providers that handle the scalability, the fault tolerant issues, but we as software engineers are tasked with designing systems that work fine. So this is how you design a job scheduler that works perfectly, and this is how you scale it. Thank you for watching, and see you in the next one.